Welcome back, Design Junkies, to Mechanical Engineering Made Simple. Today we're taking a really interesting deep dive. We're spanning pretty much the whole mechanical life cycle. We'll start with a really abstract, forward-looking stuff like design optimization, asking, what is the perfect shape? And then we'll bring it right down to the nuts and bolts, literally, of making sure power gets transferred reliably. Our mission here is basically to give you a shortcut. We want you to be really well informed about how that high-level theory, like optimization, connects with the fundamental principles you need for precision right there on the shop floor. We're connecting the big design challenges with the tiny mechanical details.
Yeah, exactly. And the material we've looked at, it really gives a good snapshot of the modern engineering landscape. We're covering, modern computational design ideas, the physics behind ultra-precise things like flexures, also industry standards for fasteners, tolerances, and the practical side of drive systems, belts, and chains. The goal is quick, solid insight. And showing how, a failure in just one little area, maybe a bad algorithm or even just a loose bolt, it can bring down the whole system.
Okay, let's kick off with efficiency. It's a huge topic. We talk about maximizing performance but using way less material. We're talking topology optimization. And this is where it gets really cool, I think. It's not just tweaking a shape. It's almost like growing a structure with an algorithm.
That's a great way to put it. We're essentially asking the software to come up with designs without our usual human bias towards, straight lines and simple curves. And the results often look, well, organic. Kind of like lattices. The impact is way more than just saving money on materials. By boosting performance and cutting waste, you get a real environmental benefit that's critical in fields like aerospace or automotive.
It sounds amazing.
Yeah.
Like perfect designs automatically. But getting there, the model the computer uses must be incredibly complex, right?
Oh, absolutely. It has to be what we call an integrated model. It needs to juggle three key things all at once. You've got complex load conditions, how the specific material actually behaves often non-linearly, and really importantly, the real-world limits of manufacturing. Can you actually make this shape? This puts a lot of the hard weight up front in the design phase. It basically gets rid of that expensive, time-wasting trial and error stuff later on.
So how does the software find these shapes? It can look pretty wild. Is it just standard finite element analysis?
Yeah. It's kind of the next level beyond basic FEA. Often involves methods borrowed from AI. Think sophisticated stuff like genetic algorithms, particle swarm optimization, things like that. These let the system explore just millions of potential structural layouts, finding the one that hits the performance targets while being super efficient with material.
Okay, if it's that powerful, why isn't everything designed this way now? Why hasn't it completely taken over from human designers?
That's a really good practical point. The big hurdle is standardization. Different fields have totally different needs, right? A part optimized for stiffness in a building is worlds apart from one designed to minimize thermal changes in, say, a semiconductor machine. So because there's no single set of rules, the best optimization method changes depending on the job. Trying to get one standard approach to work everywhere, it's still really tricky. The physics are just too different.
All right, let's shift gears. We've optimized the structure. Now, how about controlling movement with extreme precision? This takes us into the realm of flexure systems. These are really elegant, often single-piece parts that act like joints or bearings, but without the sliding parts.
Exactly. The big win with flexures is their pure elastic behavior.
Yeah.
No friction, no stiction, that stick-slip problem, and basically nowhere. Those are the big enemies if you need repeatability. But to get to the ultimate goal, like Angstrom-level repeatability, well, the design rules are incredibly strict.
Angstroms, okay, that's mind-bogglingly small. A tenth of a nanometer. Like positioning something within the width of a few atoms, what's the absolute must-have physical requirement to even get close to that?
It really comes down to the material's physics. First, you need incredibly low hysteresis in the material. It has to spring back perfectly, forgetting it was ever bent. And the absolute critical part, you have to make sure there's zero dislocation motion inside the material's crystal structure. That means designing so the stress, sigma, is kept much, much less than the yield stress, sigma yield. Normal engineering might push closer to yield. For this kind of precision, you need a huge safety margin to guarantee it stays purely elastic.
Okay, that explains why material choice is so key. Things like single crystal materials become really attractive. So once you've got the material right, how do you make sure the part only moves the way you want it to? Just along one specific axis, for example.
That's where kinematics comes in. There's a fundamental principle called Blanding's rule of complementary patterns. It's basically a geometric law for designing constraints. It says every allowed line of rotation has to intersect every constraint surface. It's the rule book that dictates precisely how motion is allowed or stopped, making sure you get just that single, predictable degree of freedom you want.
And once the geometry is defined, we can predict how stiff or compliant that motion will be. The classic example is the cantilever beam deflection equation, right? It links the shape and material properties.
Does. If you look at that formula, deflection, delta, equals the force, F times the length, L cubed, divided by 3 times Young's modulus, E times the moment of inertia, I. The key thing to notice there is how sensitive deflection is to geometry. Length is cubed. But the material property, E, is just a linear factor. It really highlights that in precision mechanics, getting the geometry right often has a bigger impact on stiffness than just picking a different material. All right, let's pivot now. Maybe it's something less exotic, but just as vital. Bolted joints. When you tighten a bolt, you're clamping 2 flanges. Now think about the flange material and the bolt itself. They both stretch or compress a bit. They act like springs responding to that preload force. A common question is, are those springs acting in parallel or are they in series?
Okay. They both experience the same preload force, but the bolt stretches and the flange compresses, so they have different displacements.
Yeah.
That means they have to be in series, right?
Exactly. They're in series. And understanding that is fundamental if you need to calculate the overall stiffness of the joint. Now think practically. What about shear loads? An external force tries to slide the 2 clamped parts sideways. What actually stops them from moving?
Well, it's the friction between the surfaces, isn't it? Generated by that high clamping force from the preload. It's usually not the bolt shank taking the shear load directly.
Precisely. Friction does the heavy lifting for shear. If you have really high shear loads, you can't rely on friction alone. That's when you need to add things like separate dowel pins, or maybe use special shoulder bolts designed specifically to take that sideways load. But none of it works if that initial preload isn't correct.
And getting that preload right, that's tricky.
Yeah.
Using a torque wrench is common. It's easy. But the sources we looked at confirmed it's definitely not the most ultra-repeatable way. Too many variables like friction under the bolt head and in the threads.
It's really just an estimation based on torque, not a direct measurement of the tension in the bolt. For real precision, you'd want to measure the actual stretch of the bolt or maybe use strain gauges, but that gets impractical or expensive pretty quickly. If you can't measure that preload accurately, you're basically guessing about the joint's reliability. Verification is key. And speaking of verification, moving from forces to geometry, we need ways to check that our parts are made and assembled precisely.
Which brings us to a real classic tool for checking angles,
Yeah.
the 10-inch sine bar. For anyone listening who hasn't used one, it's a precision ground bar with 2 cylinders exactly 10 inches apart, used on a surface plate with gauge blocks.
It's such an elegant tool because it turns measuring an angle into a simple linear measurement. You put gauge blocks under one cylinder, creating a right-angle triangle. The 10-inch bar is the hypotenuse, and the stack of gauge blocks, let's call it height h, is the side opposite the angle you're setting or measuring.
And here's the mental shortcut every machinist knows. Because the bar is 10 inches long, to find the height h needed for a certain angle, you just take the sine of that angle and multiply by 10. Or even simpler, just find the sine and shift the decimal point 1 place to the right. No complex calculations needed right there on the inspection table. It's brilliant for quick, accurate checks.
Yeah, that ability to translate a mathematical idea into a practical, repeatable measurement is really the heart of precision engineering. And underpinning all this verification are tolerance fundamentals. You have standards like unified threads, metric M profile threads, and those basic classifications of fit, clearance, transition, interference fits. These define the essential boundaries for how parts mate together. Controlling those tolerances is what makes mass production actually work reliably.
Okay, we've got structurally sound parts, precisely made and joined. Now, let's talk about actually transmitting power reliably. Let's look at synchronous belt drives first. Things like timing belts. They're crucial when you need precise speed ratios or timing.
Right. When you're sizing one of these systems, a key calculation is the operating torque, Q. You figure out torque, Q, in pound inches by taking the number 63,025, multiplying that by the shaft horsepower, and then dividing the whole thing by the shaft RPM. And importantly, you generally base these calculations on the smaller sprocket, the one that spins faster, because that's usually the limiting factor for torque capacity.
And belts don't always see a perfectly smooth load, right? So you need to build in a safety margin, a service factor. What's typical?
Yeah, the recommended service factor is usually somewhere between, say, 1.5 and 2.0. If you've got really harsh conditions or lots of shock loads, maybe constant starting and stopping, you definitely want to lean towards the higher end, towards 2.0, maybe even more, just to prevent early failure.
What usually causes problems with these drives in the real world? What makes them fail or perform poorly?
By far, the biggest issue is drive misalignment. It comes in two main flavors. There's angular misalignment, that's when the shafts aren't perfectly parallel. And then there's parallel misalignment, where the shafts are parallel, but the pulleys, or sheaves, aren't lined up in the same plane. Both of these create really big, unnecessary forces trying to push the belt sideways. That leads to overheating, uneven wear, and definitely more noise.
Speaking of noise, are synchronous belts just naturally louder?
Historically, yeah, they tend to be noisier than, say, V-belts. That's because you have rigid teeth meshing together. But manufacturers have been working on that. Some newer designs, like the Paragrip GT3 drives mentioned in our sources, they're significantly quieter. They have refined tooth shapes that mesh more smoothly, so you get high power density but less noise.
Okay, let's switch over to chains now. Chains often pull double duty, right? Power transmission, but also used a lot for conveying things. When does a chain absolutely need replacing? What's the telltale sign?
The definitive limit is all about chain elongation, but specifically the elongation caused by wear in the pins and bushings where the joints articulate. For a chain used in power transmission, that stretch, measured over a length, must be less than or equal to 1.5% of its original length. For a conveyor chain, you get a little more leeway, up to 2% elongation is acceptable. Go beyond those limits, and the risk of the chain jumping teeth or just breaking goes way up.
And that wear is why lubrication is usually so critical, and also why we have specialty chains designed to minimize that need, right?
Absolutely. Take something like Lambier roller chains. They're designed to be lube-free. They use special burnings made of sintered metal that are impregnated with oil, and the pins have special coatings. The result, especially at lower speeds where keeping standard lube in place can be tough, is potentially much longer. Wear life may be up to 30 times longer than a standard chain in some cases.
What about really tough environments, like around water or even salt water?
Yeah, for corrosion resistance, especially against water, you have options like WP roller chains. These use a special mechanical coating process. The key thing here is that it's a mechanical process, not chemical plating that often involves heat. Avoiding high heat means the chain parts keep their core hardness and the tight fits between pins and plates, which are crucial for maintaining the chain's strength and wear resistance. Heat treatment during plating can sometimes compromise those properties.
Oh, okay. So wrapping this up, what's the big picture from this deep dive? We've covered a huge range. From using algorithms to literally grow optimal shapes, to controlling motion down to the atomic level with flexures, and then ensuring power gets from A to B reliably with the right belts and chains. It's quite the spectrum.
It really is. And I think if there's one core takeaway for you, the designer listening, it's about synthesis. It's understanding that the abstract math, whether it's a topology optimization result or that cantilever deflection formula, it's only truly valuable if you can also control the smallest physical details on the ground. You could have, theoretically, the most perfectly optimized part shape imaginable. But if you fail to control the stress in a flexure, keeping sigma much, much less than sigma yield, or you ignore the proper thread fit tolerance on just one critical fastener, that one small oversight can undermine the entire beautifully designed system. Precision engineering really means mastering the micro-level details to make the macro-level performance actually happen.
That's a really powerful thought. The perfect theory needs perfect execution, right down to the smallest detail. Go forth and keep exploring this fascinating, interconnected world of precision engineering. We'll catch you on the next deep dive.